Good morning, everyone. Thank you for attending this class. My name is Devadipta Dey. I'm a researcher here in MSR, and my background is actually the intersection of robotics, reinforcement learning, machine learning in general. And today I'll be talking about and trying to give you a quick overview of what is the state of the art in AutoML for neural networks, right? And automatic neural architecture search. I'm hoping to make this much more informal, discussion-oriented. So feel free to ask questions. This is obviously not supposed to be just a talk that I'm giving. This is supposed to be much more classroom style, and then hopefully we can all learn. And also, like this, and as you will see, this is a pretty hot topic. There's lots of open problems, and this is also very tech company, definitely very Microsoft relevant, because we have Azure ML, and we would like to have AutoML offerings as well, and kind of potentially make us generate a lot of revenue. So before I begin, okay, even more. So how many of you would you say would be, at least the people present in the class, as a show of hands, would be comfortable with, let's say, convolutional neural networks or recurrent neural networks, and okay, that you have used it or heard about it, or at least at a very basic level understand one. Okay, good. And then maybe even played with some in TensorFlow, PyTorch, CNTK, etc. Okay, good. How many of you would say that you're comfortable with terms like MDPs, POMDPs, hidden Markov models, basics of, let's say, reinforcement learning, policy gradient methods, reinforce? Okay. The reason I'm asking is because reinforcement learning gets used quite a bit in many of the papers that you will come across today, right? At least in neural architecture search papers, and it's a little bit important to at least understand the basics of policy gradient methods in order to appreciate what those papers are doing. And ultimately, we will I'll make the case that, like, RL may not be the best paradigm for doing neural architecture search, in spite of a lot of high-profile papers that you would find if you did a literature search. And all the latest results are actually confirming that, which is not very surprising, but sometimes that's how communities move, right? We have collective DNA and memory. So what is, just to formalize, what is neural architecture search? So this, for example, is the table which shows you the architecture for DenseNet. Now, DenseNet is, how many of you know what DenseNet is? Okay, so ResNet? Okay, much more people. So okay, great. So ResNet and DenseNet are not that different. So ResNet came out of MSR Asia about 3 or 4 years ago now. It has definitely a great architecture where the basic idea was that, hey, skip connections and the ability to predict identity is a good idea, right? So ResNet looks, let me see. I'll use this part of the board because that part of the board will be obstructed by the dais. So let's say I have like a few layers, and I have an input image, or anything, some input X. Let's say it's an image, usually a convolutional neural network. This is a standard feed-forward network. These things can be like, convolutional, pooling, like max pooling, average pooling. Then sometimes there are like, reduction operations because we want to downsample usually the pooling will do it, but in order to sometimes we will have like dimensionality reduction operations. Same over and over repeated, like, and then what ResNet said, hey, it's good to have these skip connections. Why? Because then the network is allowed to choose its own capacity, because if the network realizes we actually don't need this layer, we can just like make this bypass this completely and learn nearly very tiny weights or zero weights here, learn identity there, and that allows you to have a lot of flexibility. Then DenseNet came around, I think CVPR 2017, and they're like, you know what? Instead of connecting, why don't we connect every layer to, instead of it being connected to everything before, to only the one before it, let's connect it to everything before it, right? So this guy gets connected to this as well as this gets connected to this, and this, and so on. And that's what DenseNet did, right? Because, which is, and they showed really great results, but it requires for you to have done a lot of work playing with these kind of networks. And then if you think of oh, why are these specific numbers the things they are, right? Like, why is this dense block output size 7 cross 7? Who said that the best thing to do is to have in this dense block on the fourth dense block, we should have 16 of these layers, then 32 of these layers in DenseNet 169, and so on and so forth. And I was having this when I was visiting MSR New York, and I was talking to John Langford, and John Langford does a lot of theoretical ML as well. And John looked at this block we were talking about. We were actually starting to think about AutoML, and this is April of this year. And John was like, I have no idea how I would come up with this, right? And I wouldn't be able to come up with this either. Like why is it that this specific set of things in sequence gives you a great result, right? And you could be like, okay, it builds upon we found somehow magically ResNet works really well, as opposed to things which came before ResNet, like VGG, AlexNet, etc. And so we connected everything to everything, and that's how it came about. But and we just did the work and found that it performed really well. But that seems very unsatisfying, right? If I give you a new data set which is not images, which is not ImageNet, which is not let's say MS COCO data sets, and many of you work in production environments where your data sets are your customers' own unique data set or data sets that you encounter as a byproduct, as a side effect of the product that you work on, which are not those standard data sets that academia, vision, machine learning community, or speech language community have the standard data sets on which they are hacking away, right? So you would like to not have spent 10 years of your life gaining intuition and in neural network architectures in order to come up with great performing, state-of-the-art beating neural architecture on your own, right? And it seems like not just very unsatisfying, not the right way to make the field progress. And so ideally, we would like to just do things automatically. I should be able to, the dream is, let's say I were to come up with ImageNet. I give you ImageNet or some big data set that you care about, and you want to just throw it on, let's say, Azure and say, come back in 2 days and we will give you the state-of-the-art architecture, right? Or not even 2 days, 1 day, or maybe you set a budget, I'm willing to spend $10,000 in compute. This is a very important data set for me or my client, and I want the best performance on validation or held out test set once this $10,000 runs out. In fact, there are computations now that are being run which are models like this, where it's if you give what is the best architecture or how well can you do in $100 worth of cloud compute, right? And as you can imagine, this is a very important problem because the vast majority of the world do not hold PhDs in deep neural architecture hacking, or have not spent 10 years building a lot of intuition. So we want to be able to truly democratize all of this, and also find good principles of how should that table be generated without having to just try things by hand, which seems very inefficient. And so that's why this field or subtopic has become quite important. And to show you how important and hard this has become, I'm going to take you to show you this web page maintained by Frank Hutter and his group. This is a very good website, by the way, if you want to keep up with AutoML stuff, automl.org. They are doing an excellent job. So this is the following list of papers related to neural architecture search. And these guys are doing a lot of work just to compile every paper that's coming up on arXiv. With, not every paper, not all papers are of as good quality, and some of those papers some papers are much more serious than others. I highly recommend reading this survey. I'll put it in the slides. It's a good way to get a quick introduction into what's actually happening. Hopefully, you will take away a lot more from this class as well. But what I want you to take off is, so this survey came out in August, and we are like middle of October. Already there are 3 more papers, and if you look at like the list in 2018, like in the first 10 months of this year, and this list is going on and on and on, and let's see. Yep, it ends here. Right? So in 2018, neural architecture search has really taken off. And in fact, if you look at 2017 is big, but not as big as 2018, and 2016 is even smaller. And 2015 is like, downright, there were just 2 papers, right? And then 2012, then nothing happened before that, and then 2009, 8, 2, et cetera, right? Like, so 2018 seems to be the year for neural architecture search, and I'm not surprised because, hey, we are actually starting to do really well on many tasks individually with our individual combined experiences and expertise and armies of researchers and engineers. So there's this big effort now to automate this. So let's see if I can get my cursor back. Got it. Yeah, and if you want to not read the full list, which you should not, is go read the survey article. It's very well written, and I highly recommend it. So before we go and dive, I'm going to talk about 4 or 5 papers today, which are representative ones. And as it happens in almost any field, many of these techniques have epsilon differences across papers. It's like, oh, I did it this way. This other paper just tweaks that and does it this way. They find that it gives a little bit of benefit here and there. So what I have tried to do in this class is actually pick 4 papers, which are like different techniques. Like think of them as the principal axis of different techniques. 2 of them will use policy gradient methods, and then the rest will not, right? And the other 3 will not. But the first really serious papers, all of them actually came from Google, Quacklay's group, and who were trying this from 2016, 16 onwards, and they all used reinforcement learning. And some of them also used evolutionary search. So let's give you a very quick primer on what I really mean by reinforcement learning, which will be relevant to this class. Now, obviously, reinforcement learning is a topic of its own. People spend their lifetimes on it doing research, so I'm not going to be able to cover anything almost in 15 minutes that I have reserved for this. But I want to just give you enough background so that you can appreciate, why are the techniques that are being techniques, why were they chosen, why they may not be the best, or maybe they are the best, we just haven't got the right formulation. But all the initial results, serious results, came from using model-free RL. Okay, so we will do a quick digression into slides that I have. Let's see. Okay, and then I think there's a way to make this full screen. View. Okay, perfect. So this is a friend of mine from my grad school days, and so he gives a really gave a good lecture. So I stole some of his slides, but all the work was done by Jeff for these slides. So you must have heard, like people who have maybe at least heard about reinforcement learning or planning of this term, like Markov decision process, right? So Markov was this Russian mathematician who really formalized what a lot of the groundwork on which reinforcement learning is based and planning methods are based. And so what is a Markov chain? Right? So these are very simple constructs, but they are very powerful. So a Markov chain has a finite number of discrete states. And let's say in this simple example, you are at S1 and S2 are your only two states. We have probabilistic transitions, which you can think as the more general form of deterministic transitions. So if, for example, if I'm at S1, then with some probability 0.9, I will spontaneously move to S2. With probability 0.1, I remain at S1, and similarly for S2 with 0.8, I might go to S1 or remain at S2, right? And all that is, and then there's this Markov property is that in order to know, for you to know what is the likelihood of you ending up at any other state, all you need to know is what state you are currently in, right? And you don't need to know history of previous states. It doesn't matter how much time you have spent at S1 or S2 before, as long as you know what state you are in right now, which is either S1 or S2, it completely determines where you are going to, the chances of where you are going to be next, right? And that is what is often called as the Markov property. And not a lot of things in the world are Markovian, right? For example, weather is not Markovian, right? Our stock market is definitely not Markovian, right? Like you just knowing the stock price today doesn't tell you anything about this, tell you a whole lot about stock prices tomorrow. You might, in order to actually have any chance of doing good modeling, you want to know the history and probably even more information, right? Similarly with weather. But it turns out that a lot of things for which Markov assumptions hold admit really efficient algorithms. And then there's this thing called hidden Markov model. What hidden Markov model is exactly the same as Markov chain, except you don't know what state you are in. Like the state is hidden from you. And for example, a good example that gets used, that HMMs get used a lot in for formalism and to model things is speech-to-text translation. So imagine all you get to observe is the audio. And your algorithm's task is, the computer's task is to translate this from the sounds waves that are coming in from picked up by your microphone to text. So you don't actually get to see what were the words that were being spoken. You have to somehow infer them from the observations that you are getting, right? So there's this new thing you will see, which is called O. For example, if you are at S1, so for example, if you were actually saying the word, let's say Tuesday, right? You actually don't get to see that what the word Tuesday is. You have to infer that, that is your task, but you get to hear the sequence of sound or audio waves that the microphone gets, and hence you actually don't know whether you are in S1. All you get to see is O1, then you get to see, I don't know, Wednesday, so you get to see O2, and you have to then figure out from the sequence of observations you are getting what was the sequence of states that you might have been in, right? And it turns out that there are algorithms which are very much like dynamic programming, which give you what is the most likely path sequence of states you would be in given the sequence of observations you saw, right? In order to solve HMMs, that's which it. But again, note that both in HMMs and Markov chain, there are no actions, right? Like state transitions are beyond your control. Like when you get speech, you get the speech somebody spoke. You don't get to control what is the next word based on where you might be. MDPs. Now this is the fun stuff. The MDPs have everything. So they have states. And in this case, in this example, I'm again showing discrete states, but in all of this, continuous states are just as fine. You can represent continuous states. And you have actions here. So if I'm in S1, and if I take action A1, with 0.3 probability, I go back to S1, and with 0.7 probability, I go to S2, right? And similarly for S2, so on and so forth, right? And you have this new concept called rewards. So Rewards are, if I'm in state S1 and take action A1 and I were to move to S2, I might get some money, some credit, right? And for example, if this is a video game, if S2 is the state that is the winning state, right? If I am, and somehow if I am for example, I don't know, chess. Chess has a lot of states. Go, for example, has a lot of states. And my aim is to somehow meander through state space by taking actions, where actions are like I get to move my chess pieces and end up in the state where I have or the subset of states where I captured the king of the opposing party, right? So that would be the state I want to go. And if I were to be able to somehow successfully achieve that before my adversary, I get a big reward, which is I get to win the game. So, and this is what you would see in reinforcement learning, is that there's this aim of maximizing the reward, the transitions you get as you move around in state space. Sometimes you also get rewards incrementally. For example, in chess, a good surrogate intermediate reward might be how many pieces of the opposing party you are capturing, right? So you might have heard of this term called sparse rewards. Like winning the game all the way at the end is a very sparse reward. We might want to get some intermediate reward, and that's where people get into all kinds of reward engineering. But ultimately, no matter what you do, you are defining an MDP. An MDP comes up with what is your state space, what's your action space that you can do at every state. Then you have a transition model. In video games, typically, for example, in chess, in the game of chess, my transitions are deterministic. Like if I choose to move a piece, my action is move pawn to E4. You move the pawn to E4. It's not like with some probability you move the pawn to E4, right? So it's deterministic. It just means with probability 1, that action will succeed. There are many cases in which things can be probabilistic. We'll get into that later. So you have transitions, and then you have rewards, like for transition, and you don't, and all of the states are visible to you. You get to know which state you are in. Right? Like in chess, you know what is the state. It is the relative position of all the pieces on the board. That's all the information you need. And usually it's Markovian. It doesn't matter how you arrived at the current position. In order to win, what matters is how you are going to, what you are going to do next, right? So your policy, your game playing policy does not have to depend upon history, which is very nice, because otherwise your policy tends to become very hard to find, because your state space will blow up. Okay, so let's see. Then we have the partially observable MDP, where it's the same as MDP, except now you don't know which state you are in. And again, you will find you have this thing called observations. And observations are only for example, chess is not a POMDP, it's an MDP. Go is not a POMDP, it's an MDP. A good example of POMDPs, for example, is robot motion planning or localization of, let's say, self-driving cars. When you are in downtown Seattle, you might find that your GPS becomes very noisy, or the ellipse uncertainty becomes very big. You are between buildings, GPS doesn't work. So your location is no longer directly observable. But you might have a belief. You might have an idea of based on oh, I saw the Starbucks, I see Capitol Hill signs that so because that's your observations, that's all you can see. Your GPS is now pretty useless, but based on what you are seeing, which are your observations, you may be able to have some belief over what states or what set of sequence of states you might be in, right? And you might be like, oh, if I see the Space Needle and that on my left, I must be in this neighborhood and whatnot. So this is again, you look at your observations, try to figure out what state you are in, and then if you are given the belief of what state you are in or states you may be in, you try to plan your path to go to your friend's house, for example. So that's what POMDPs in general are much harder to solve than MDPs. Usually you can't solve more than toy problems in a principled manner, so that's why we have job security. Lots of research goes here. Yeah, and here's a very helpful chart. So depending upon are your states completely observable and whether you have actions or not, you either have a Markov chain, HMM, MDP, or POMDP. Like if nothing else, take this away from this class. This will help you out a lot. If you're not reinforcement learning or planning experts, this comes out as very handy to have a mental model. Okay, so now while I will leave that on the board. So let me see. Okay, I have this. So we're going to focus on MDPs, right? And an MDP, is defined as in order to define a particular MDP, you have to define the state space, the action space, the transition probabilities between states, and the reward function, right? So this, and usually for completeness, you might have S naught, which is or probability of S naught, which is what is the start state you are going to start, and it may be a single state S naught, or it may be a probability distribution over a bunch of states. So if I define this, I have defined an MDP. So, what does it mean? Let me see. For people who are maybe familiar with planning, what does it mean to say that solving an MDP? Take a guess. You might hear this word a lot, we have to solve this MDP, solve this. What do you think it means?
Maximize the reward we get.
Absolutely, right? You might want to come up with a policy where a policy is, there are 4 kinds of policies, but policy is a mapping. The simplest policy is a mapping from state to action. What I want is, give me a policy pi, which I'm going to just use the symbol pi, which is very common notation in reinforcement learning literature, which says, if I'm in a current state S, what should I do? To do what? To maximize my expected reward, where when you take the policy pi, so let's say you start out at S naught. Let's say you took action 1, then, and let's say you have let me just define an action space. You get to go up, down, left, right. And I don't know, you're playing some Tetris or some grid search, room navigation game, where there's a pot of gold hidden away, and you have to figure out what is the path I should take in order to go there, right? Like a shortest path problem, right? So, which is exactly an MDP. Now, I am going to take action A1. I will get some reward. Then let's say I will hit S1. Then my policy might say, hey, what am I doing here? I'm going to take action A2. I might take A1 again. I might go to S2. I might take A0 this time, so on and so forth, right? So this is basically I'm going to call this the squiggly. There's a more mathematical name for it, which I never can pronounce. So this is essentially a trajectory. So I have a policy which I play out from S naught, and I go all the way, I play it out, and let's say I play it out for n steps or some horizon, let's say capital H, until I reach the goal or time, or I'm stopped, that's my budget, and that gives me a particular trajectory, and every time I do a transition, I get to see a reward. My aim in solving this MDP is to come up with a policy such that the sum of all the rewards is maximized, right? That give me a policy pi such that if I were to take these actions according to pi, so at S naught, I do pi of S naught. Pi of S naught says, hey, you should take A1 here, take A1. At S1, I do pi of S1. And it gives me this, right? And my aim is to maximize 1 to H, this. So pi would be argmax over, let's say I have some parameters theta of my policy, which is what I'm writing here. Argmax over theta, whatever theta star I get, the pi star corresponding to this is the policy which maximizes it. Now, there are various ways. What I have actually done is jumped a lot ahead and said, like, my policy is parameterized by my some parameters theta, right? And these theta are usually also, like, in deep reinforcement learning, the theta comes from the parameters of your neural network, and in linear policies, you may have a linear regressor or a classifier if you are doing, like, discrete number of action steps, which all it is saying is that give me the theta such that if I were to play that policy out, I will maximize this, right? So that usually these, like, for example, shortest path problems are a special case of solving MDPs. What is your MDP there? Your MDP there is, like, let's say the grid world of states, and actions are how you can move between them. Let's say you can go left, down, or up, right, and you want to like, minimize the cost of going from a start state to the end state, which can also be posed as maximizing the negative of that cost. And you do dynamic programming, and indeed solving MDP is the optimal way to do it, is to solve big giant dynamic programming problems. But there's usually a big issue with that. Go ahead.
What is T here in this program?
T? T is the transition.
I mean, in this particular grid search.
Grid search, yeah. It's like, so if I'm at a particular, it's basically a table which says that if you are at state S1 and you take action A1, which is like, let's say, go up, right? Like, let's say this is my grid. I am here. Then T basically tells me, T tells me, like, if T of S1, and this, let's say, is called S1, and if I were to take action A0, what is the next state, S prime, that I will end up at, right? And in this one, like, if I take the action up, I go up. If I go here, so on and so forth. T just defines me where I go, my dynamics.
Mm-hmm. But in some problems, there could be several states you can go, right? So, and probabilities. Yeah.
Yes. So the one I'm showing here is a deterministic state transition probability, that if I take A naught, you go to S prime. But it could be like, you actually get probability of S prime, a distribution, right? And where, for example, in robotics, it often happens that if I give a command to the robot doesn't execute that exactly. Instead of actually going all the way straight up, it kind of sort of goes up. So you may actually end up in different states. So let's see. Okay, I'm already at 11. We the thing that happens is, and this is a very common confusion whenever I'm interviewing interns for summer internships at MSR, I often ask them this very simple question that, okay, this is define me an MDP. They all define me the MDP just fine if they are reinforcement learning background. And I ask them, tell me what makes a problem a reinforcement learning problem. Like, what is missing in which makes, so the shortest path problem that I described to you is a planning problem, right? Like, I can just do dynamic programming in a discrete space. You can also do it in continuous space, which is a detail, but I do dynamic programming and I can solve it. So then what happens when why RL? Why does the entire field of RL exist? Like, who can tell me what is missing in an MDP to make it an RL problem?
Possibly feedback.
Sorry?
Feedback.
Feedback. Can you tell me more?
Basically, you receive some sort of a feedback after you make an action, after you make a transition. And based on that feedback, you take a next action or take another transition. And
So-
trying to maximize the reward.
Okay, you get so the intermediate reward, you can get that in, like, MDPs as well, right? So the reward is known in an MDP setting, right? So for example, if you are making progress towards your end state in the shortest path problem, you can get an intermediate reward, right? Like, and also because you know exactly where you are, you know that, right? It's usually something else. Reward is usually not the problem, although that was a good guess. There's not a lot of symbols there, so by process of elimination, there are 3 left. Sorry?
E is not known. Transitions.
Yes, that's right. So this thing, if you don't know what T is, then it's a reinforcement learning problem. And so think about chess or AlphaGo. Everybody has seen Go and AlphaGo, and people have been DeepMind used deep reinforcement learning, but deep doesn't matter as much right now as reinforcement learning. Why do you think that is who can explain what is not known, how the T is not known there?
Because the state is a state of the board, and there are so many states.
So many states is fine. Like, it just means that my state space is really, really gigantic, right? But how is the transition not known?
So do not know the reverse exactly.
You know the reward.
No, opponent moves, right?
Exactly. Like when I take an action, like, let's say you are white and you put a dot on the board and you took an action and you got to see, like, the next state of the board. But what you don't know is what black will play, right? Because you don't know that, that makes it like, you don't know transition. You don't know the exact state or the sequence of states that will evolve, result as an effect of what you did, right? And that's why it's no longer a planning problem, and that becomes a reinforcement learning problem. And all the reinforcement learning problems have this, like, flavor of interacting with a simulator. In the case of Go, the board is the simulator itself, which is very nice, and which means that if I can solve my play in the simulator, then I can come up with a good policy in the simulator. I have actually solved the real world problem. It's just because so happens that video games like Atari, Go, chess, etc., all these things have the world is what you have defined it to be. Yes.
Yeah, but analogy with chess is not really a precise. Because see, modern chess game use alpha beta, so I know the transition. In other words, before I move, I do alpha beta, and I find the possible responses. And in fact, my alpha would be influenced by that.
Hold on, I don't think I understand the alpha beta part.
Alpha beta. So it's not MDP. What actually there's a RL in modern, like AlphaGo, for instance. It's only tip of the iceberg. It's all machine learning behind, like the heart of it. It's alpha beta search, meaning that you look, you make a move, and you look what the possible response would be up front.
Like Monte Carlo tree search.
With certain depth.
Okay. Yeah.
And so for you estimate, in fact, your own reward.
Yes.
And clearly, you have some heuristics for that's called strategy.
Yep.
How you define those very finite number of moves.
Yeah.
And then you get it.
Yeah.
RL is using only for optimization of this process, not more than that. In other words, chess is not RL problem.
I would disagree because you still don't know the transition.
No, I know you disagree. But
Yeah, but like, whether you formulate it as an RL problem or not is a separate issue. And actually, I will show in neural architecture search that it should not be formulated as an RL problem. It's just that a lot of people did, right? Is that if I assume that in my chess, I have the state, actions, transitions, and rewards, like, and say that I don't know the transition because I don't know what thing is, then I can do RL, right? And even in AlphaGo, for example, you do the value function estimation by doing every time before you have to play, you simulate forward many steps, right? And then the neural network is guiding you to cut down your, for example, your branching factor. Because you
I understand, but Dev, let's be specific. The question was, what makes a problem an RL problem?
I would argue that chess is absolutely an RL problem.
Well, this is exactly where we disagree.
I think this is pretty binary, actually. I don't think this is a philosophical debate.
It's not philosophical debate. It's pretty binary.
Yeah,
It's not.
yeah. I'm pretty sure it is. So now that we have a policy, so now that we have at least got a flavor of what makes a problem a reinforcement learning problem, now we are going to, let's see, go across one method very quickly. And before we, I don't know how much time I will have to fully derive this. So I'm going to write down so remember we were looking at we want to maximize the full reward of our policies, that as they go across, how much what is my cumulative reward, I want to maximize that. And I'm going to write it down as j theta, right? And I'm going to not use discounting terms, is my sum of my Ri, t is equal to 1 to my big horizon. I want to maximize that. My policy goes from S to A. I'm going to have a stochastic policy in policy gradients, where instead of going from states to a particular action, I will go from state to a probability distribution over action. And what I would want to do is take the gradient of my cumulative rewards, and then P, where I'm going to use squiggly for my trajectories, R of squiggly. I'm going to use another pen. Where R of squiggly is, remember, I go from S naught, I take some action, then I go to S1, then I take, let's say, another action, so on and so forth. And then I'm just going to sum up all the actions I receive. That I'm going to is this big R over here. So what I really want is why do I want to take gradient of this? Because so that I can do gradient descent in the parameter space of my policy, and until I come up with, or gradient ascent, until I come up with the policy which is really good, right? Which is like a parameterization. If you are, for example, if I'm using a neural network, then my neural network gives me really good rewards. When I use that to do policy. Now I can, okay, let's see. So I can then rewrite this as gradient of theta, sum over R tau, where I'm just using this is the space of all possible trajectories that you could take through your state space. Now this seems really bad because okay, the set of all possible trajectories is exponential in my horizon, and then I might have a very large state space. But things are not as bad as they look, because this term, probability of you taking a trajectory, given your current parameterization of your policy, can be written down as okay, so it can be written down as this, right? It is just I have gone through all my a particular trajectory, and I am writing down that what is the probability that I'm in state of the beginning state times the probability that I will take action A naught given that I'm in S naught, given my current policy, and then I keep multiplying it times probability that I will be in S naught given that I took action A naught in S naught, so on and so forth. And then this thing can be written down as just this term. Okay, I can move now this term inside, like this gradient with respect to theta, and you will see that this will come out as sum over RT, gradient of theta, probability of this given theta times R squiggly. I can just move that inside because the other term will be 0. And then it is gradient of tau. I'm going to multiply and divide by right? I'm just multiplying and dividing by this by this quantity, and then okay, I'm going to use this. I can take this summation and this thing out, and then just write it as an expectation again of probability squiggly given theta. So this is just like, rewriting it again as expectation. And then you will see that because I'm writing this term, look at this term, like gradient of probability of a trajectory divided by the probability of the trajectory. This I can rewrite as this. I can just write it as log of probability, because if I take gradient of this, then it will give me this term back, which is a really nice trick, because once you have written it as in terms of log, I can then expand this out, right? Remember, like this, a probability of this given this is this term, right? So if I take log of a bunch of things which are products, I get additions, which is very nice, because most of these, it will come across as like, like this, like log of sum over all the time steps, P of st given st minus 1, comma at minus 1, plus sum over t log phi at comma st times r of squiggly, which is just, you see, I'm collecting all these terms separately and then collecting these other terms separately. And if you see, if I put the gradient term inside, none of these depend upon theta, right? So all of these will go to 0. And only this depends upon theta. So if I rewrite everything a little bit nicely, I'll get a theta is x. So there are variants of this depending upon how you write it. This is called policy gradient theorem, right? So it basically says like how you are going to take gradient of your policy with respect to your parameters of your policy theta. And remember, your policy has to be stochastic such that you do well, like it's gradient with respect to this reward function, but all you need to see is that you need to be able to take, in order to compute this, take gradient with respect to theta of your policy parameterization, which is very nice. And one very nice thing to note here is that you're not taking derivatives of your state distribution. This comes in super handy, right? Which is very nice that the math works out that way. So now we can, okay, if you keep that in mind, so I actually haven't given you an algorithm. I just told you how to take gradients. If I know how to take gradients, then theta nu is basically like, my theta old. I can come up with like, basically a gradient descent style thing, plus some step size alpha times gradient with respect to theta, j theta, right? I can do this and come up with, and keep on iterating over this until I am sick of it and I converge or I find a good policy. Okay, so now you must be wondering, like, we haven't done actually any neural architecture search up to now, but don't worry. If you understand the policy gradient theorem, the first 2 papers are 10 minutes. And we'll leave that thing over there. Here's some study material. We'll go over this back. So I want to begin with this one. So what happens here is you can pose neural architecture search. It may not be wise to do this, but this is what happened in 2016 as neural architecture search was posed as a policy gradient problem, like was an RL problem, where your state space, so let's go through the state space. Your state space is the space of all possible neural architectures. Or you define some state space, and all the possible architectures that it admits is your state, is the space, right? So every S is now a particular architecture. Now your actions are basically you get to select, right? Like, you get to move from one state to another. So you can transition arbitrarily almost, except that you don't know what actions would result in you getting good rewards. And to make it even harder, so you know the reward function very well. The reward function is, I want you to give me ultimately a good architecture that results in very good, like, let's say accuracy on the data set I care about. I know that for a fact. And so if I pose my problem as this reinforcement learning style, policy gradient style reinforcement learning, then I'm going to have a policy, and my policy here is going to be, they're calling it the controller, which is an RNN. And what this controller will do is it will sample an architecture A with probability P. Remember, why is it sampling an architecture? Because our policy is probabilistic. We need a stochastic policy to make the policy gradient theorem work. So that's why people are like, okay, we are going to sample an architecture. We are going to sample an architecture with probability P. We are going to train a child network with that architecture all the way, like, do your regular neural network training until you see your accuracy or negative of your error, and then you compute the gradient, right? And okay, now the question becomes, how am I going to compute this gradient, which is here, right? Which I gave it here because I have that expectation term. And let me, okay. So what this paper has done is basically written out that math in again, but instead of expectations, they have replaced it with the sample estimates, right? So this is what we are trying to maximize. So instead of squiggly, they have written it in this. It just makes it takes more space. So and I want to come up with parameters theta such that my expected reward is maximized of my trajectories that I will take. And this is that same derivation of how it actually came about to be. This is also the algorithms that this admit called reinforce, and there are many, many variants of reinforce today. And since I can't evaluate this expectation exactly, I'm going to turn it into a sampling problem. I'm going to just sample, and this is the sample estimate, right? So what I'm going to do is I'm going to use my controller to sample architectures, train all those architectures, then go see what the rewards I got from that, plug that back in here, right, where your k equals 1 to m are basically all your things that you have been sampling. This is just 1 by m to get the average, which is your sample estimate of that expectation, and then take a gradient step of the RNN. And this I know how to do. Why do I know how to do? Because I can do backprop, right? I know how to take gradients of my parameters in a neural network. So I'm going to replace, so my controller is going to be an RNN, which is going to sample architectures. Now the question becomes, how are you going to sample architectures from an RNN? So this is where the domain expertise comes in, which is not actually that hard, is I'm going to unroll the RNN, and at each step of the RNN, I'm going to sample in sequence, like as I'm unrolling the RNN, the filter height, the filter width, stride height, and stride width of a convolutional layer. So basically, a layer's definition is given by this, right? Like, so this is one, 2, 3, 4, 5. These 5 numbers define me a convolutional layer. Like how many what is the height, width, what is my stride height width, and the number of filters it will have. So if I can sample this, then the next 5 unrolling will be another layer, right? So I can stack up, like, okay, I ran the RNN, let's say 20 times, so I get a 20-layer neural architecture, right? And then I can take that 20-layer neural architecture, go and train it on another GPU, see the reward I got back, come back and plug it into my policy gradient theorem, estimate by doing sample estimates, because I'll have many of these, and then take a gradient step on the RNN, the controller that is happening. And that's exactly what they did. They just posed neural architecture search as this reinforcement learning problem. And in order to help speed things up, this is where all the engineering comes in. You are going to have the parameters of your RNN are going to be saved in like many parallel parameter servers, such that your controllers are then have many replicas. This is all this you need to do is because the hardest part in all of this, the most time-consuming part is coming up with many samples to get this expectation. And remember, a sample here means sampling an architecture, training it all the way to the end. So for example, if I give you ImageNet, this will take you 3 days, right? So one sample is extremely expensive. So hence, if you have 8,000 GPUs and your manager is okay with you burning for $20 million on that, then yeah, go do this, right? Pose it as this way, take and run this. This is all the engineering you need to do to have any hope of getting enough samples and doing this. Then there is some engineering that you need to do in order to reintroduce skip connections, right? Because this is important again because this gets a little bit tricky, is, we know that on images at least, on ImageNet CFAR10, ResNet and DenseNet style architectures which have skip connection tend to do well. So if you design a search space which does not admit skip connections, like in the first one we saw, then that is going to be, you know that you are leaving a lot of human expertise out. Like we know skip connections help. Really, they dramatically speed things up and all lots of good stuff happen. So I'm going to introduce this 6th unrolling, which they are going to call an anchor point, whose aim is just to sample, if you are in layer n, which of the n-1 layers to connect to. Right, so and that's something you just sample the skip connection. So there's this defined. Now you are back into DenseNet space. So all possible skip connections to things before you are now a part of your search space. So this is where search space hacking comes into play, because if you make your search space too big, you are not going to, your state space is gigantic. You are not going to be able to search everything, and so yeah. And then when you are doing, so a lot of, okay, now there's more hacking needed in order to make sure that networks that you are sampling are valid networks. Like remember, just because I come up with a few numbers, because all the RNN is doing is sampling 6 tuple or 5 tuple at a time to define layers and connections, but those things may not actually work together, right? For example, in layer n, if I say the number of filters and the stride height width is certain, it expects a certain tensor size to go in, right? Because and if that doesn't go in, it just because the layer n-1 is completely different shape and it's not compatible, you can't do the matrix multiplication, right? So in order to make things actually work, these are the hacks you do. Like one of the hacks is you must have skip connections. They are concatenated along the depth dimension. That way you don't have to worry about that if you, for example, if you wanted to do summation, this won't work. It might happen that you have tensors which are completely different shapes. How do you sum them? Then if a layer is, but if you are just concatenating, it works out just fine no matter what you have, as long as you pad everything to make the concatenation go through, right? If something small comes and something big is there, you just pad everything by zeros, make it the same size, concatenate them so that now you have a nice big tensor, and then you feed that forward. Okay, so you do all this, and you use a lot of electricity, and you come up with. So this is on CFAR10. So the CFAR10 is this image data set. It gets used a lot in all this NAS work because unlike ImageNet, it's much smaller than ImageNet. So you actually, all the evaluations that you are doing, like sampling architectures and training them and then taking the gradient step, usually can be done in let's say half a day if you have very fast GPUs and you architect them well, right? So you don't have to wait for 4 days for ImageNet, right? And various variants of their algorithm, they come up with good results, right? 3.6, 5, which is pretty at that time was good. These are the number of parameters that the architecture that they found which performed well. had. Okay, and then they also did something on like language modeling task, just to show that our method doesn't just apply to images. It can work on like Pentry Bank, which is a language data set. I'm not an NLP expert, so I can't tell you a lot about it, but they show at least that they have in here they have this term called perplexity. It's like, think of it as a surrogate for accuracy, and lower is better, and they achieve actually one of the lowest, and this was great, right? So at the time, this actually started off this neural architecture search, the massive amount of work, the exponential gradient we are seeing in this number of papers and work that is being done here, because they're like there was suddenly, by just doing automatically complete search, yes, with a lot of GPUs, we can find actually human beating architectures automatically. This is great news because that means I don't have to have 10, 15 years of neural architecture hacking experience in order to develop intuition. Okay, but one of the things that actually the details are in the paper is they used actually like almost 8,000 GPUs running for months, and that's at least what they reported. And that would mean I will take up all of Philly. For those who use Philly right now, it only has 10,000 as of today, right? So this will be hard for me to do, even if all of Philly was dedicated to me for 6 months, right? Fortunately, things have become much, much better and efficient. And so there was this other paper that came out in February this year, the first versions, and it's called Efficient Neural Architecture Search, or ENAS. And it achieves actually much. So this beats the first NAS paper that we saw. These numbers in the first NAS papers were around 3.6, 3.7, 4. This is much lower on CFAR 10. On Pentry Bank, it's even the previous NAS had 62.4. And this is the best part, right? One single NVIDIA 180 Ti GPU, search takes less than 16 hours. For them, it was thousands of GPU hours, right? And so this is almost 3 magnitudes reduction in search time. So this is okay. Now, with one desktop GPU, I can actually achieve better results than what they could do before. What is the trick? The trick is that I'm going to share computation along all my experiments. So, okay. If you noticed in the previous work, what was the big time-consuming step? The big time-consuming step is not actually doing that computation once you have all the rewards and the samples of all your rewards coming in, because that's a very tiny step. Updating the controller takes probably a minute or two. The big times things was training all those things in parallel to completion to get your samples, right? Like I sample one, send it off to a computer, go train, sample another architecture, go train, sample another architecture, go train. Now, all these things take a lot of time and a lot of compute. So, and this is why the number of GPU hours is massive. And because everyone is doing forward prop and back prop independent of each other. Now, this idea will sound like barbaric, is that, and totally crazy, but it somehow works here, is that what if I don't send everything off and run them independently? What if I have this big giant computational graph, and I sample from that big giant computational graph, but share all the weights? And do all the training and backprop for, so basically, imagine, so this is a toy example. So let's say this is my big computational graph, and this basically defines my search space. And I'm going to say that I'm going to sample this, this red set of arrows is one network, right? And then so that I'll put aside and I'll put it over here. Then let's say I come up with a blue set of arrows, which may be like this, some other sample from this. That's my another network, and so on and so forth, right? And then, but instead of training them all on different computers with different GPUs, I'm going to train them all together and just share the weight. So for example, if this edge is common between the two sampled architectures, they will actually share the same tensor. They will not or share the same parameters, sorry, not the tensors. They will not actually be completely independent. So, but this seems very bad, right? Because you should be like, but if I were to actually train them separately, the set of weights that I will get be connecting 1 and 2 may be useful only to that architecture because it has a certain topography and it will specialize, and it should not be very useful to this. And this is why, like, if you were to just suggest this to me, I would be like, that sounds crazy. That is going to make everybody really suboptimal because things should specialize for their architecture. But somehow that's not true. And then this was like a big head-scratching moment where, okay, they don't have proofs, theoretical proofs here, but they show that, like, hey, our motivation is basically multitask learning, like, with a neural network, how you can give it many different tasks, and it tends to, like, generalize better if you make it do multiple tasks at the same time. And based on those multitask motivations, we started along this path, and we find that we can actually do very well. And so, for example, like, here is how they do, like, the sampling. And here again, they're still doing policy gradient methods. They still have a controller, which is RNN. But, like, the layers, so this is like for recurrent neural networks. This is how a particular cell looks like in them. This is the search space coming in. And you have all these operation options, and they're showing, like, what got sampled. And you can read the details. The details are really boring, but yeah. So, for example, if you want to design convolutional neural networks automatically, then you can you fix this skeleton and outer structure, and you can sample what layers each should be doing this, right? And this is the other trick that they also did, is that instead of there's this term called macro versus micro. You will hear a lot when you go across NAS papers. What macro means is search means I give you nothing. You start with like a very small network, and I'm not going to enforce any topology order, right? Like you can grow the network, you can do whatever additions, subtractions you want. You can sample from this big giant search space, any arbitrarily shaped big network, and that's fine. And we'll like search in that space. In order to make things a little bit more tractable, what people start doing is called microsearch. So they fix. So for example, oh no, I rubbed it. Okay, I'll use it this way. For example, okay. Remember ResNet? ResNet seems like a good idea, right? What if I define my search space to be like this? That, hey, image comes in, I'm going to fix the ResNet architecture, the outer skeleton. This will be my macro architecture. I'm going to fix it. I'm not going to let this be a degree of freedom. And then what I'm going to say is that what should go here, right? And all I'm allowing the network to, this whole sampling business search procedure to do is tell me what kind of layer I should have here, what layer have here, 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 so on and so forth. And in order to make things even more tractable, all I'm asking is that I may say that all of these will have the same layer, but what that layer type should be, whatever layer that should be, I'm sampling here, I'm going to replicate it exactly here, right? So these are all ways of reducing the search space. But notice that in order to do this micro or cell search, because you're just searching the cell, and you're fixing the outer skeleton design fixed based on something good that some human expert found, you are relying on the fact that there is a human expert who has given you a good macro, right? If for images, a lot of research has been done. For language, a lot of research has been done. So you may have good macro architectures that you can focus on. Whereas, if I give you a completely new data set, Evan, or maybe data sets in different domains for which there is not a lot of prior work, you may not even know what is the right macro, right, to begin with. So there is this, in order to make things tractable, there is human domain knowledge injection into a lot of NAS papers to make the search space good. Good meaning like we know that this kind of thing works, so what is the argmax within the scope of these kind of things, right? And then that's what a lot of papers do. So they use that trick. They use the trick, we are going to share parameters. We are not going to run everything on different components. And notice as, okay. And they come up with like, so this is called ENAS, various tips and tricks like cutout and they, in order to come to that number, but they're extremely efficient, right? Okay, so this is, for example, this is a discovered network. ENAS is also able to do like macro, so they show this is their macro one result, and I don't know, I would have never hand designed this architecture by myself, and this is actually does really well on a lot of image classification tasks. Notice how the skip connections like are all over the place. Why they would be is just something that they found, the automatic search procedure found good. These are cells, like remember this cells thing? These are weird cells that are discovered automatically. Again, I don't think like, if you had asked me to design one, I would have ever come up with one such wonky ones. Okay, so the first two, so these two papers were reinforcement learning based, right? So where they basically said, we are going to frame this as like, an interaction problem. We don't know what the transition is going to be, and our rewards are differentiable. So we are going to have this, rewards are not differentiable because I don't know how to differentiate reward with respect to the parameters of the controller. I only can differentiate my reward with respect to the individual thing, the networks that I'm going to sample, so I need to use policy gradients. Okay, so and that's how these papers came to be. Now, there are a vast amount of papers which actually don't use reinforcement learning or specifically policy gradient. So one is like, called progressive neural architecture search. I'm going to skip a lot of the details and like, and give you, because we are going to run out of time, and give you the intuition, where the intuition is, I'm going to grow networks, and I'm going to grow, and there is no controller, there is no RL. But what I'm going to do is I'm going to start from a small set of, these are parent networks which may be like almost 1 or 2 layers. I'm going to I'm going to evaluate them, see which one of them like do well. Like I may like add then based on which ones do well, I may like expand them. So this is almost like will remind you of like genetic algorithms or evolutionary search style algorithms. Like based on if there are good parents, then the ones which like did well, the children of them are promising, might be promising. We are going to only then see which children did well, then take only a k subset for the next set of parents for the next generation, then again expand, and then again cut it down like all the non-promising one, keep only the promising ones, and at each step, like these kind of steps, I'm just adding layers, right? I'm sampling layers and adding them, and remember like all the big time goes in neural architecture search in like especially like okay, I have all these like networks here. Each dot is a specific network architecture. Training them takes a lot of time. So what they said is like we are going to have this predictor which is going to try to predict by just looking at the parents' performance and the mutation that was added in order to create the children, what the performance can be like without training them. Right now, this becomes like this chicken and egg problem. So the algorithm looks very much like you train this for a little bit, gather a little bit of data, train another predictor. It could be another neural network or a tiny neural network which predicts how well these things would do based on their little amount of training we have done on them and past history of other fully trained networks they had, and take only the top k. Right? That's how you take the top k without fully training them. That's what saves you a lot of time. Okay, and it's a very simple procedure. And compared to like NASNet, which was like the first paper and whatnot, they like so this is progressive NASNet. They do well. Their search time is much lower. It's an idea. I wouldn't get hung up on the numbers too much. They also tried on ImageNet. They don't really search on ImageNet. What everybody does is they search on CFAR. they find a good architecture, and then they just replicate all the cells, they make the network bigger, and then they train it on ImageNet. So that's the standard trick, because doing the search directly on ImageNet is going to take you a lot of time. Okay, so I'm going to take 3 more minutes and run through darts, because this is my favorite paper so far. This is under review at iClear right now. The reason I know it's under review, because iClear, if you know how the conference works, is completely open review, except the authors are anonymized. This is a really cool paper. No controllers, no intermediate performance prediction, which has problems because you can diverge. It outperforms everything else before it, as far as I can tell. It achieves the state of the art on CFAR 10, and as well as on, I think Pentry Bank in a single GPU day. Very nice. And this is where, not casting problems blindly as RL problems really helps, right? And this is okay. The trick here is I'm going to do a continuous relaxation of a discrete search problem, optimization problem. Remember, my aim is to somehow go through the space of neural network architectures and find a good one. Neural network architectures are discrete. They may be similar to each other, but they are not continuous. It's not continuous space, right? If this is one architecture, the architecture next to it differs from it in, let's say, a particular layer or a particular parameterization of some layers or whatnot, right? And even it's hard to define what does next mean, right? It may mean small edit distances. Here, what we are going to do is imagine this is a cell. And again, darts mostly does cell. I don't think they do macro as far as I could tell. And I am going to try to figure out within this cell, if there are 4 things I'm going to have in my cell, I'm going to try to first connect what should be the operations that connect these cells, right? And I'm not going to make an assumption of sampling from this and from all possible operations, coming up with certain cell architectures and then evaluate them by training them. I'm going to assume that all these operations can coexist, right? So this is kind of the mother cell. And what I'm then going to do is there are weights, then put weights on these operations. That how likely is it that 1 and 3 should be connected by a convolution layer or by a pooling layer or by I don't know, a reduction layer or something, right? These are and then I'm going to put alpha 1, alpha 2, alpha 3 weights over them. And this gives me this another graph, right? So which is the continuous relaxation of this discrete derivative problem otherwise I would have. Then I'm going to run this bi-level optimization. I want to find good alphas, where alphas, remember, if an alpha's weight is very good, that means this green line is thicker. If the alpha's weight is small, then it means that this probably is not the right operation to connect between these two. And what I'm going to do then is first run an optimization over alpha, right? Randomly initialize the weights, do backprop over alphas only, holding all the other weights constant, and see which ones start to win out. And this is just a visualization of these alphas. And then I'm going to stop my optimization over alpha, and then depending upon which ones have whatever weight, optimize over the actual neural network architectures that are admitted by this particular instantiation of alpha, right? So this is an architecture, except is that, I'm going to connect 1 to 3 very strongly via pooling, very little via let's say a convolution layer, and very little by a reduction layer. I'm keeping all possibilities on the table at all times, except that the weightage gives me which one is more likely than the others. Given this architecture, then I'm going to actually optimize for the parameter values inside it. And then I will go back and forth. I will do a little bit of alpha, then a little bit of the weights, little bit of alpha, little bit of the weights, so on and so forth, until one of these alphas starts to become really matter a lot, and then I'm going to take that out as the argmax architecture, right? So the nice part about this is that you don't have a separate controller to train via doing policy gradient things. all the architectures search is amortized by forward, like the forward and backward propagation operations are amortized across all the architectures all at once, right? Which is very nice. Similar to in-as tricks, but even nicer because you are keeping all possible architectures all at the same time. And then at the end, you are just taking the argmax out. So basically, this is like what the algorithm looks like. Don't worry, is that update the weights by descending down, like hold alpha constant, update the weights, and this is just your standard backprop operations. Then you update the architecture alpha by descending down, like the space of alphas, hold W constant, and which is again just backprop, but on this metagraph. And then at the end, once you have found which one is you replace all the edges by just the one which is the argmax, like the thickest line that remains. And if you see, like, they really have some of the best, like, results, like, in just like, 4 days of GPU search time, they get to 2.83. ENAS gets slightly, like, is pretty comparable. But I think, like, the final numbers are better on this one, even though ENAS just searched 0.5 days instead of 4 days here. But I think so far, I think this is the best method because the numbers are just really, really good on everything. And you only need a single GPU. And there are already extensions on darts that I'm seeing people start to work on. In general, it's a good idea. Do not do RL. Look at the numbers for RL. The search cost, which is what should really worry you, is not just the final numbers on CFAR. Is look at this. This is like burning all of Philly dedicated to you for like 6 months. That's the kind of thing you're looking at, and that's just for like CFAR, right? And just not a very good way of finding architectures. And then there are many, many open problems. Like all the current papers, they show either CFAR 10, 100, ImageNet, Vision, or one NLP dataset. Are we, like, it is the entire field converging to a few datasets? And then there's also this, like, search space hacking by assuming that we have a good macro and going around doing cell search in order to make the search space tractable. So what happens when you don't know what is the right macro architecture? So you can't do micro anymore. Here's some teaser results from our group where we actually do, we grow neural networks by adding layers. There's lots of tricks we use to make this happen, including for people who were at the exploit day yesterday. We use a lot of explore-exploit trick algorithms. We directly search something called the Pareto front, which is for every accurate, as much accuracy you can get no lower in terms of parameters. If you plot that gives you a Pareto front. So we search around the Pareto front as we are training, and we show that, like, we can come up with, like, extremely. We can do ours is macro over there with extremely, like, small amount of search, pretty good numbers. We are much more general than even, like, darts is doing. Like, darts is doing micro, we are doing macro, and we are able to get good performance with compared to darts and all the other Google papers. So these are teaser. We are still running lots of experiments, but yeah. Happy to take more questions, or we are over time, but luckily we don't have a class right away. But I think, as, like, my takeaway has been by just looking at NAS is that the days of human domain experts, like, doing a lot of, like, engineering and trial and error are soon going to be over. And it should be over. Like, we should not be sitting there like, okay, maybe I should replace this layer with this, send the job out, come back in 2 days, see what happens, right? It's just very unsatisfying, especially as we start using neural networks everywhere for new data sets and tasks, right? Yeah.
So the methods that use parameter sharing, do you know like how do they compare to the ones that do not do parameter sharing in terms of performance? Like, are they actually losing anything by sharing?
No, that's the surprising thing, right? They actually don't lose; they do better, and they actually like both like whenever if even darts you can assume is doing parameter sharing because all the nets are there. ENAS, the efficient NAS is doing parameter sharing. They actually do better, and their search time is like 3,000 like 1,000x less, right? Which is the super counterintuitive result, but if you believe their results, and I believe they are good people, that's true.
So is it possible that this kind of like sharing and overlaying on top of multiple architectures is kind of reinforcing some signal in the architecture that gives you more confidence that this is the right one to choose?
Yeah, definitely. Like because like if certain kinds of weight values, like parameter values, are like because one way to think about it is like all these different architectures are enforcing regularization on the same like common edges, right? Like they are not letting the edges overfit to the different architectures if you had trained them independently. And so, yeah, it's the multitask regularization effects are coming into being. And because these weights have to do well across all the architectures that share that edge, right? So it might be actually helping. Like I don't may have to do a lot less regularization by hand. And also, I don't want to give the impression that this is all magic and okay, we should just implement darts and we are done. There's a lot in order to get those numbers. There's a lot of domain engineering that goes on. Like the reason if you saw in those tables, like cut out this with path augmentation and drop path. This is all like tips and tricks that only if you go and look at their Python notebook, you will find like okay, this is not as simple as just fit and then come back. You have to do all these tricks to get those numbers. But that's just like, researchers who are like, oh, mine is better than yours, getting into that game, right? Yeah. Yeah.
You might have mentioned this already, but what is it exactly about darts again that allows it to train so quickly?
The fact that so they are not really, they don't again, they're implicitly sharing all the parameters, which and the weights on architectures, right? So they have this like continuous relaxation of this discrete search space. So any given like subgraph is a specific architecture, right? So, and these are all, but they're all kept. They're all kept all at the same time. It's not that you sample from this, train, and then come back. Everybody is kept all at the same time, and you do this like alternating minimization over the architecture parameters and the parameters over the network weights that admits them. That's yeah, it's the sharing trick that makes it. Cool. Feel free, meaning I'm in the same company, so feel free to ask me, email me questions and whatnot. And I think the slides are already up on the SharePoint, so you can get the slides. That survey paper is very nice if you're interested. It gives a lot of open problems out. It's very honest. I like that.